In mathematics, the study of groups is old and established. It is conceptually the easiest of the three algebraic structures that you learn about in a first course on algebra. Although mathematicians often like to start from definition, it is not clear on the outset why this definition was eventually settled upon. Starting from a set which we call the group, every element must obey certain rules that guide their play. Although these rules can look like mere symbol manipulation, behind them is a structure that comes from the thing that groups actually study, the symmetry of objects, in all the ways it can manifest. Saying something is symmetric commonly means that there are two halves that look the same and are mirrored, but this is only one possible way of being symmetric. What we are saying when something is symmetric is the fact that we can draw a line through the object, and that both sides are the same but mirrored. But there are also other things we can do with objects, where at the end the object in some sense looks the same. Let's take for an example the square with labeled vertices. The square has many symmetries. We can fold it over horizontally, vertically, diagonally through AC, diagonally through BD, or rotate the square clockwise or counterclockwise. Saying that an object will look the same after such a transformation is vital. Also, there should be some way to undo the symmetry. And it does not matter if we apply two symmetries and then another, or first one symmetry and then two others. These three properties are actually all that the formal mathematics in the definition of a group mean. These rules make more intuitive sense when we have started from considering the symmetries of geometric objects and what properties should hold for these symmetries. Now we can consider objects which have more or less symmetries than a square, and we will know that the same framework which we work with will still work in the manner we expect symmetries to behave like. Of course, since we are doing mathematics, we are not limited by what we can draw on the page, or even make a 3D model out of. This general way of thinking about symmetries can be done abstractly. We can think about symmetries which an object should have, without having to visualize the object directly. Without a picture of the object, we can think of all possible states the object can be in while still being the same. For example, for the square, we can give all the possible states a number instead of keeping track of the vertices. This is actually how we think about a group in practice, and this specific set of states is denoted by D4, which we call the dihedral group on 4 vertices. Then, starting from some state, we can apply a symmetry, for example counterclockwise rotation, where we call doing this action to the square alpha. We look at which state we end up in, and draw an arrow labeled alpha between the two states. Now, nothing stops us from doing alpha again, and looking at which state we are in now. If we do this again, we notice that after applying alpha 4 times, we end up in the state we started from. In this case it is clear, since by rotating a square 4 times, we are just back at the beginning. Something which we immediately see is that we cannot get all states by just applying alpha. We could take another symmetry that gives us a new state, for example the horizontal reflection, which we call beta. Notice that by applying the group action beta, we are in a state where we have not been before. Applying beta again, however, gets us back to the start. Now, from the new state beta gives us access to, we can repeatedly apply alpha to get new states again. Notice that in fact by just applying these two symmetries, we can get all possible positions of the square. When this is the case, we say that alpha and beta generate a group. Putting this diagram in a bit nicer way, and forgetting about the actual geometric structure of the square, we can look at which arrows we can draw for beta, which we have not drawn before. This actually gives us quite a nice way to visualize D4. Since taking a state where we are in and a state where we want to go, we can find a path in the graph that takes us there. Note that starting from any point and applying alpha 4 times, we end up at the starting point. Traversing through this graph actually gives us a closed loop, and the same for applying beta twice. There is in fact another type of closed loop we can make, by applying alpha beta and then alpha beta again. This uses both generators. Note that any other loop is essentially combinations of these 3 simple loops. Finding such a closed loop is the same as doing nothing, which is also a symmetry since the object looks the same after doing nothing. If we write this as E, we can write these closed loops as alpha to the 4th equals E, beta squared equals E, alpha beta equals E. There is actually something interesting about this graph. Picking any vertex in the graph, we can apply the same generators and we end up at the original vertex. So the same loops are closed for every vertex, and it feels like we can describe this graph in a way that does not require us to draw it in its entirety and finding all types of closed loops. So forgetting about which vertex we start at, since it does not matter, we can describe this graph, which we call a Cayley graph belonging to the group, in this bracket notation: alpha beta, alpha 4th, beta squared, alpha beta, alpha beta. We call this the presentation of the group, with the left hand side called the generators and the right hand side called the relations. It turns out that these three ways to describe the group D4, considering all states geometrically, making a graph describing how we move through states, and only writing down which closed path we can make inside the graph, are equivalent, and are all sufficient to tell us how the group behaves. This is quite remarkable, since the information needed to depict all states is considerably more than the presentation. It is clear how we can get from the presentation of a group to the consideration of all possible states of the geometric object. We start with a point and draw closed loops from this point described by the relations. Then, we keep drawing arrows at all the new points until we can make all closed loops from all points. Now that there is a graph, we can count the amount of vertices we have, which is the number of states, called the order of the group. And we have a description that tells us how the generators act on these states. Doing it the other way around, however, is not as easy. How do we know which symmetries to pick to get such a nice looking graph? Is this always possible? And is there essentially only one way of doing it, or can we get different presentation by starting with a different symmetry? As is often the case with such compelling questions, it is unreasonably difficult to answer for all cases. We do know, however, that the presentation of a group is not always unique. For example, taking two different symmetries of the square, the vertical flip C and the diagonal flip D, we can also end up in every state, and the Cayley graph is different. Hence, the presentation CD, C squared, D squared, CD, 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 CD is also a presentation of D4. A hidden assumption with which we have been working up till now is the fact that after applying a symmetry a number of times, we will eventually loop back to the start. This makes sense when thinking about the possible states of a geometric object, but we have abstracted away from these objects already a while back. What happens if we pick a symmetry and we can assume that it will never get back to the start? This is actually called a free group, and the presentation can be written as alpha. As our previous procedure tells us, we start with a point and keep doing alpha, but we will never end up at the start, which means that this is an infinite graph. Notice that we can also start by undoing alpha from the start, which gives us an infinite graph in two directions. We can label each point in this graph by counting how many alphas we have done from the start, to depict the infinite graph in a nicer way. As can be seen, this is essentially counting from 0, with alpha adding a +1 and the inverse of alpha adding a -1. So what we have here is just a complicated way of writing the integers. This points out some hidden symmetry inside the integers that we might not have thought about before, and shows us that the integers can be considered as an infinite group, more specifically, a free group with one generator. Doing the same procedure with two generators, we can try to construct a graph in this way. Starting at some state, we can do two things, A and B. Then, the states we end up with are not the same state, so in both cases we can do both A and B again. Since there are no relations, no combinations of A's and B's will give us a closed loop. This leads us to being able to do as many steps as we want without ever circling back, and gives us the Cayley graph of the free group with index 2. Taking more and more generators and constructing the Cayley graph of the free group with index n gives us these nice fractal pictures. Taking the bigger picture, we have made a geometrical picture from abstract information of a group, from which we can get information about the group that was difficult to see from only the presentation. You can imagine that there are many different ways to geometrize properties of groups. This is actually a topic that is still studied in modern mathematics and is called geometric group theory.